The universe is trying to kill you in ways you've never even thought about, from solar storms that melt infrastructure, to rogue planets hurling through the dark, to theoretical particles that could rewrite reality itself. Today, I'm breaking down the most dangerous stuff in the entire universe, ranked from survivable to absolutely universe-ending, starting with something that almost destroyed modern civilization 12 years ago: coronal mass ejections. On September 1st, 1859, telegraph operators across the world started getting physically electrocuted by their own equipment. Wires sparked. Paper caught fire on desks with nobody touching it. The machines kept working even after being unplugged. That was the Carrington event, the most powerful solar storm ever recorded hitting Earth, and it absolutely fried the only electrical infrastructure humanity had at the time. Here's the thing, that was 1859. Telegraph wires were the most advanced tech on the planet. Now imagine that same storm hitting today. You don't have to imagine. In 2012, a solar storm of equal or greater power ripped through Earth's exact orbital path. We missed it by 9 days. That's not a metaphor. Earth was literally in a different spot in its orbit when the blast crossed through 9 days earlier, and we're looking at a completely different world right now. Modern coronal mass ejections travel at up to 3,000 kilometers per second, roughly 7 million miles per hour, and release energy equivalent to 1 billion atomic bombs. A direct hit today would cause an estimated $2.6 trillion in damage to power grids and electronics worldwide. No ATMs, no supply chains, no hospitals running on grid power. It wouldn't end civilization, but rebuilding global power infrastructure would take years. And that's just the sun throwing a tantrum. But at least the sun stays in one place. Rogue planets don't. ROG planets. There are an estimated 200 billion rogue planets drifting through the Milky Way right now, not orbiting anything, not illuminated by any star, just entire worlds, some the size of Jupiter, hurling through total darkness at tens to hundreds of kilometers per second, and we can barely see them coming. Here's the thing, the real danger of a rogue planet isn't a collision. It's something much quieter. If a Jupiter-mass rogue planet entered our solar system on a crossing trajectory, its gravity alone could pull Earth out of its orbit within 6 months. No impact, no explosion, no dramatic fireball. Just a slow, silent gravitational eviction into the void, where temperatures drop to nearly absolute zeros and every ocean on Earth freezes solid. And the worst part, detection is still incredibly difficult. We've only confirmed a handful of nearby rogue planets, with some candidates spotted as close as roughly 20 light years away. But with 200 billion of them out there, the odds of spotting one on a collision course with enough lead time to do anything about it are basically zero. But here's where it gets weird. Some of these frozen wanderers might not be completely dead. Researchers argue that rogue planets with active cores could maintain subsurface oceans through geothermal energy alone, meaning life could theoretically exist on a world that has never seen a single photon of starlight. Entire ecosystems thriving in permanent, endless darkness. It's a strangely hopeful thought, but if rogue planets are the universe's silent assassins, antimatter is its most efficient weapon of destruction. Antimatter. Antimatter is the most efficient explosive in the universe. And that's not an exaggeration. It's a physics fact. When antimatter touches normal matter, both are completely annihilated. Not partially, not mostly. 100% of their combined mass converts directly into pure energy. No waste, no byproduct, nothing left behind. Let me put that in perspective. A single teaspoon of antimatter making contact with a teaspoon of regular matter would produce an explosion on the scale of Hiroshima. Scale that up to a coffee cup and you're flattening an entire metropolitan area. 1 kilogram meeting 1 kilogram of normal matter releases the equivalent of 43 megatons of TNT. That's roughly 2,000 times more powerful than the bomb dropped on Nagasaki. So naturally, we should be terrified, right? Here's the thing, CERN, the most advanced particle physics facility on the planet, has produced less than 10 nanograms of antimatter in its entire history. That's the total, ever. Accumulating enough for any kind of weapon scale event would take millions of years at current rates. We built the most dangerous substance physically possible and we can barely make a speck of it. But the real mind-bender isn't the explosion potential. It's the fact that antimatter exists at all in such small quantities. The Big Bang should have produced perfectly equal amounts of matter and antimatter. Equal amounts that would have instantly annihilated each other, leaving behind nothing. No stars, no planets, no you. Something gave regular matter a tiny, unexplained edge, and physicists still have zero idea what it was. Your entire existence is a rounding error that nobody can explain. And if a physics accident feels unsettling, wait until you hear about the dead stars that can kill you from 600 kilometers away. Magnetars. Picture a magnetar sitting where the moon is right now. Every credit card on Earth, wiped. Every hard drive, gone. Every MRI machine, destroyed. Not from an explosion, not from radiation, just from the magnetic field existing near us. And that's the tamest thing a magnetar can do. These are neutron stars with magnetic field roughly 1 quadrillion times stronger than Earth's. Let that number settle for a second. 1 quadrillion. Their surface temperatures hit around 10 million Kelvin, and only about 30 confirm magnetars exist in the entire Milky Way. They are rare and they are absurd. Here's where it gets genuinely terrifying. At just 600 kilometers away from a magnetar, the magnetic field would reach into your body and physically strip iron atoms from your hemoglobin. No dramatic explosion, no cinematic death. Your blood just quietly stops functioning at the molecular level. You die because your biology literally can't hold itself together anymore. But the real showstopper happened on December 27, 2004. The Magnetar SGR 1806-2 O released a burst with an initial spike lasting just 0.2 seconds, a fifth of a second. In that blink, it released more energy than the sun puts out in 250,000 years. And here's the kicker, it was 50,000 light years away from Earth, and it still measurably ionized our upper atmosphere, from halfway across the galaxy, in a fraction of a second. These aren't objects that play by normal rules. They make the sun look like a nightlight. And the terrifying part, magnetars are just dead stars with strong magnetic fields. They're not even the most dangerous collapsed stellar objects out there. If you enjoyed this video and want to see more, click the video on the screen now. Wait, we're not done, not even close. Because if magnetars bend the rules of physics, black holes break them entirely. Black holes. You already know black holes are terrifying. Everyone does. But knowing they're scary and understanding what they'd actually do to your body are two very different things. Let's start there. If you fell toward a stellar mass black hole, the gravitational pull on your feet would be so much stronger than the pull on your head that your body would stretch violently. This is called spaghettification, and it's not a metaphor. Starting around 100 kilometers out from the event horizon, tidal forces would begin pulling your head and feet apart. By the time the process finishes, the distance between where your head was and where your feet were would exceed 1,000 kilometers. You wouldn't die in one clean moment. You'd be drawn out like taffy over hundreds of kilometers of empty space. But here's the part that actually haunts me. Time dilation near a black hole isn't science fiction. It's measured, confirmed physics. As you fall toward the event horizon, time slows down for you relative to everyone else. You could experience a few seconds of free fall while centuries pass for the rest of the universe. Everyone you've ever known, every civilization that existed when you started falling, gone. And you wouldn't even feel it happening. Now the good news. Sagittarius. A star, the supermassive black hole at our galaxy's center, sits 26,000 light years away. It's 4.1 million solar masses of pure gravitational nightmare, but it's not coming for us. The real threat would be a wandering black hole drifting through our solar system. It wouldn't need to swallow Earth. It would just destabilize planetary orbits, potentially ejecting us into interstellar space within weeks. No heat, no explosion, just darkness. And black holes don't even die. Hawking radiation technically causes them to evaporate, but a solar mass black hole would take 10 to the power of 67 years to disappear. The universe is only 13.8 billion years old. They will outlast everything, but at least black holes require proximity. The next thing on this list can kill you from billions of light years away. Gamma ray bursts. Here's something that should keep you up at night. A gamma ray burst can release more energy in 10 seconds than the sun will produce across its entire 10 billion year lifespan. Not a fraction of it, not a percentage, more, all of it, compressed into a flash shorter than a commercial break. GRB 090423 alone unleashed roughly 10 to the 53rd power ergs of energy. That's the equivalent of about 100 supernovae detonating simultaneously. One single event producing the firepower of 100 exploding stars. And these things happen constantly. The Fermi telescope picks up 1 to 2 gamma ray bursts every single day, all from distant galaxies. So far, distant. There are two types, short bursts lasting under 2 seconds caused by neutron stars slamming into each other, and long bursts lasting more than 2 seconds triggered by massive stars collapsing in on themselves. Both are catastrophically powerful. Both are essentially the universe's most violent death throes pointed in a specific direction like a cosmic laser. Now here's where it gets terrifying. If a gamma ray burst occurred just 3,000 light years away, which is well within our own galaxy, it would sterilize every living thing on the exposed side of Earth within hours. The radiation would punch straight through our magnetosphere, shred the ozone layer, and leave the surface completely unprotected. Some researchers have even proposed that past mass extinction events on Earth could have been caused by nearby gamma ray bursts. That's still speculative, but it's physically plausible. And the worst part? There's no warning, zero. Unlike an asteroid or a rogue planet, you can't see this coming. The light and the lethal radiation arrive at exactly the same time. By the time you could detect it, you're already dead. But if a beam of energy that kills everything it touches sounds bad, wait until you hear about a substance that converts everything it touches. Strange matter. Everything we've talked about so far kills you in dramatic fashion. Explosions, radiation, gravitational nightmares. Strange matter doesn't do any of that. Strange matter just replaces you. Quietly, completely. And that's what makes it the most unsettling thing on this list. Here's the deal. Normal matter is built from two types of quarks, up and down. That's everything you see around you. Your body, the Earth, the sun. But there's a third type of quark called a strange quark. And some physicists believe that matter made from all three, up, down, and strange, might actually be more stable than regular matter. Not just a little more stable. The most stable configuration of matter possible. The true ground state of everything. And if that's true, we have a massive problem. A single particle of stable strange matter, called a strangelet, coming into contact with normal matter wouldn't bounce off. It wouldn't explode, it would convert that matter into more strange matter, which then converts more, which converts more. A chain reaction with nearly 100% mass energy efficiency, spreading through every atom it touches like an infection with no cure. The math is genuinely horrifying. A strangelet contacting Earth could theoretically convert the entire planet into a cold, dense ball of strange matter within minutes. No fireball, no shockwave, no warning, just conversion. Everything you've ever known restructured at the subatomic level into something alien. Now here's where it gets complicated. No strange matter has ever been detected. Not in cosmic rays, not at RHIC, not at the LHC. Decades of searching have turned up zero evidence. Many physicists argue that stable strangelets are extremely unlikely, maybe even impossible. The theoretical barriers are significant, but maybe impossible is not the same as impossible. And if it isn't impossible, literally nothing can stop it. At least strange matter is probably fictional. Hypernovae are very, very real, and they make supernovae look like firecrackers. Hypernovae. You already know supernovae are devastating. They're the gold standard of cosmic destruction. But a hypernova makes a supernova look like a firecracker at a nuclear test site. These are the death of truly massive stars, typically over 30 solar masses. And they release 10 to 100 times more energy than a standard supernova. We're talking 10 to the 52nd ergs. That number means nothing in isolation, so let me put it this way. A hypernova briefly outshines entire galaxies containing billions of stars. One dying star brighter than 100 billion living ones. But raw power isn't what makes hypernovae terrifying. It's what they do with that power. In 2003, astronomers observed SN 2003-DH and definitively confirmed something that had been suspected for years. Hypernovae don't just explode. They produce long gamma ray bursts as a secondary effect. That means a single hypernova is simultaneously one of the most powerful explosions in the universe and one of the most lethal radiation events in the universe. Two apocalypses for the price of one. A hypernova occurring just 1,000 light years away would sterilize Earth within hours. Not days, hours. The radiation would punch straight through our magnetosphere like it wasn't even there. And 1,000 light years is nothing on a galactic scale. Our nearest stellar neighbor is about 4 light years away. We're talking a range that includes millions of stars. Here's where it gets worse. After the explosion, after the gamma ray burst, after everything within range has been irradiated into oblivion, the hypernova leaves behind a parting gift. The remnant collapses into either a magnetar or a black hole, both of which you've already seen on this list. Hypernovae aren't just destroyers. They're factories that manufacture other entries on this list. But even a hypernova has limits. It's still a single star dying in a single moment. Quasars don't have that limitation. Quasars. A single quasar outshines its entire host galaxy. Let that sink in. One object, powered by one supermassive black hole, producing more light than 100 billion stars combined. The most luminous quasars output around 10 to the 40th watts of power. That number is so absurd that no analogy does it justice. It's not just bright, it's the brightest sustained energy source in the known universe. And the way they kill is even worse than the light suggests. Quasars fire relativistic jets, beams of superheated plasma traveling at over 99.9% the speed of light. If one of those jets were pointed directly at Earth from even a few light years away, every complex organism on the planet would be dead instantly. Not over weeks, not over days. Instantly. The radiation exposure would be so extreme that the atmosphere wouldn't even have time to act as a shield. It would just be over. Here's where it gets strange. The first quasar ever identified, 3C273, was confirmed in 1963. It sits about 2.4 billion light years away and is still one of the brightest objects we can observe. But the most distant quasars? Over 13 billion light years out. When we look at them, we're seeing light from when the universe was less than a billion years old. These aren't just dangerous objects, they're time capsules from near the beginning of everything. And before you file quasars away as ancient history, consider this. The safe version of a quasar is sitting right at the center of our galaxy. Sagittarius A star is a supermassive black hole that's currently quiet. Currently. It has shown signs of periodic activity, flaring up in ways that remind astronomers it's not dead. It's sleeping, and sleeping things wake up. But quasars, for all their terrifying power, still operate within the laws of physics as we understand them. The next entry on this list doesn't, and if it ever happens, there won't be anything left to observe it. Vacuum decay. Every other entry on this list destroys things. Vacuum decay doesn't destroy things. It erases the rules that allow things to exist in the first place. And that distinction is what makes it the most unsettling concept in all of physics. Here's the simplest way to think about it. The quantum vacuum, the baseline energy state of our entire universe, might not actually be the lowest possible energy state. Think of it like a ball sitting in a small dip on the side of a mountain. It looks stable. It feels stable. But there's a much deeper valley below. All it takes is one nudge, one random quantum fluctuation somewhere in the universe, and the ball starts rolling. That nudge would create a bubble of true vacuum, where the laws of physics are completely different. And this bubble expands outward at the speed of light. Everything it touches, matter, energy, the fundamental forces that hold atoms together, all of it gets rewritten. Not destroyed, rewritten. The physics inside the bubble aren't our physics anymore. There is no shielding against it. There is no surviving it. You can't outrun something moving at light speed. And even if you could, there's nothing to run to because the rules your body operates on no longer apply. Here's where it gets uncomfortable. The Higgs boson measurements place our vacuum suspiciously close to the boundary between stable and unstable. Current data doesn't confirm we're in a false vacuum, but the uncertainty range is, let's say, not reassuring. We're sitting right on the edge, and the math doesn't rule out the bad scenario. But the real gut punch is this. Vacuum decay could have already started. Billions of light years away, a bubble could be expanding toward us right now. We would never see it coming because it travels at the speed of light. The first sign of its arrival would also be the last thing that ever happens. No warning, no detection, just existence, then nothing. But at least vacuum decay requires a random quantum fluctuation. The next threat on this list? Humans might build it on purpose. Gray goo. Every other entry on this list comes from space. Exploding stars, rogue planets, the fabric of reality itself turning against us. But this one we build ourselves. Gray goo is the theoretical nightmare scenario where self-replicating nanotechnology, tiny machines designed to build things by harvesting raw materials from their environment, malfunctions or escapes control and just starts eating everything to make more of itself. And the math is what makes it terrifying. One nanobot becomes 2, then 4, then 8, then 16. Standard exponential growth. With a replication cycle of just 1 hour per generation, you go from a single malfunctioning nanobot to the entire mass of planet Earth converted into undifferentiated goo in under 100 hours. That's roughly 4 days. 4 days from one microscopic machine to no planet. Here's the thing, we're currently nowhere near building anything like this. Autonomous self-replicating nanosystems are decades away at minimum, possibly centuries. The technology required to make a machine that can harvest environmental materials, process them, and assemble a perfect copy of itself at the molecular level is so far beyond what we have right now that most engineers laugh at the idea. Even the guy who invented the concept walked it back. Engineer Eric Drexler introduced gray goo in 1986 and later spent years arguing that proper engineering constraints make the scenario largely avoidable. Most nanotechnologists today consider it physically implausible because of thermodynamic limits and basic engineering realities. You can't just eat a rock and turn it into a precision nanomachine without enormous energy inputs and incredibly specific conditions. But largely avoidable isn't impossible, and physically implausible isn't physically impossible. The reason gray goo earns its spot on this list isn't probability. It's the nature of the threat. Magnetars don't care about us. Gamma ray bursts aren't malicious. Vacuum decay isn't anyone's fault. But gray goo, that's a catastrophe we would engineer, manufacture, and deploy ourselves. The only existential threat on this list that requires human ambition to exist. And honestly, that might be the scariest part. But even our worst inventions pale in comparison to what the universe has planned for its final act, the Big Rip. Every single thing on this list, from coronal mass ejections to vacuum decay, destroys things inside the universe. They play by the rules of physics. They operate within the container. The Big Rip doesn't destroy what's inside the container. It destroys the container itself. Here's the thing. This scenario only needs one condition to be true. Dark energy, the mysterious force driving the universe's accelerating expansion, has to behave as what physicists call phantom energy. That means its push gets stronger over time instead of staying constant. And current measurements of dark energy's equation of state sit right at the boundary where this becomes possible. Not safely in the clear, not obviously doomed, right on the edge. If it tips the wrong way, the sequence is methodical and total. Galaxy clusters tear apart roughly 200 million years before the rip completes. Then, about 60 million years before the end, individual galaxies like the Milky Way dissolve. Then solar systems, then planets, then molecules, then atoms. Then, in the final 10 to the negative 19 seconds before the rip completes, even atomic nuclei are shredded apart. Every force in physics, gravity, electromagnetism, the strong nuclear force, all of them lose to expanding space itself. And this isn't settled science. The Hubble tension, a persistent and growing disagreement between different methods of measuring the universe's expansion rate, may indicate that dark energy is not constant but evolving. If it's evolving in the wrong direction, the timeline shortens. The difference between the Big Rip and heat death matters. Heat death is the universe going cold and quiet. Everything fades. The lights go out slowly. The Big Rip is the opposite. It's the universe going violent at the end, not fading out, but being actively, forcibly undone. It's not death. It's the end of the conditions that allow anything, including death, to exist at all. That's not a threat inside the universe. That's the universe itself saying it's done. If you enjoyed this video and want to see more, click the video on the screen now.